Okay, guys, we are now recording. All right, so number one is a 30, 60, 90 with a 45, 45, 90 inside. Do you see that?
Yeah.
Okay, so do you understand that side BC would have to be equivalent to AB?
Yeah.
All right. Now that we know that, let's look at this big triangle, which is your 30, 60, 90. This is our 30-degree angle because 15 plus 45 is 60. So the big angle up at the top is our 60. This little angle down here is our 30. So if this side is 20, then this side is 10 because the hypotenuse is twice as long as the short leg on a 30, 60, 90 right triangle. Okay. Now, big picture idea, they're asking us for the length of BD. So in this case, not BD, DB, same thing. DB is going to be DC minus BC. Can't do any letters correctly today. So, we know if the short leg is 10, then the long leg would be 10 roots of 3. Now let's focus in on this not drawn to scale 45, 45, 90. If this is 10, BC is also 10. So the answer is C. Okay, number 2. You did a ton of this in geometry, so I know you got this. Volume equals edge cubed. So if the edge is 3, the volume of cube A is 27 cubic units. All right, B. B is to do 3 times the volume of a cube with an edge of 2. So 3 times 2 cubed is 8 times 3 or 24. So A is larger. A is your answer. Number 3, a square inscribed in a circle with a radius of 2 pi. What is the perimeter of the square? So I'm visual, so I'm going to sketch this. Square inside the circle. Close enough. I get the idea. All right, so if the radius is 2 pi, that means that diameter would be 4 pi, right?
Yeah.
Okay. The diameter is also the hypotenuse, or the diagonal of the square, which is also the hypotenuse of a 45, 45, 90. So this side right here, which is the side of the square, you would find by doing this divided by the square root of 2. All right, and we're to do the perimeter of that square. They're going to rationalize this, so we would multiply by the square root of 2 over 2. So we'd get 4 pi root 2 over 2. Which is 2 pi root 2. That is one side, 2 pi root 2. And how many sides do we have? 4 of them, so we would multiply by 4 and get D, 8 pi root 2. Any questions about number 3? Okay, number 4 is just move things around game. So, on number 4, if this flipped up here, it would fill in that. If this flipped up here, it would fill in that. So really, it's a semicircle, right? The shaded part could be denoted as a semicircle. So it's half pi r squared, because it's half a circle. B. Okay, real quick. I stayed here Friday night until 6:55-ish. When I shot right over to the ball game so I could watch the dance team perform. To my surprise, the dance team was not performing. So I got there in time to be early and to, chill, literally, for a little while before the game started. But before I left, I graded lots of things. I entered lots of things. So if you did not turn in SAT warm-ups, it is denoted by a missing grade. So if you have SAT warm-ups for me today, you can turn those in. I Well, you may have been the only one absent. Was anybody else absent Friday?
Not us.
Nope. All right. Okay, let's go ahead and check your homework. I'm going to hit pause on the video while you're checking, and I'm going to check for completion. Okay, so let's take a look at a couple of these. I told you guys it would be good if we didn't distribute. So if you left this one as 2 times x plus 10, that is fine. Especially here. It's best to not distribute because then you can actually see the x at the vertex. It has to be in this factored form to see that x in the vertex clearly. And this is 2, 2, which wasn't really much of a check step because this one is 2, 2. Can you tell you switched them? You did. Was there another one? Or just those 2?
I think it was just those 2.
Okay. Any other questions? Yes, ma'am.
For number 5, I left my answer as y negative 1 equals the square root of 3 x plus 4 divided by 2 minus 5. Is that wrong?
Like it.
Oh, you like it?
Yeah,
Okay.
because in this form, you can clearly see the vertex is negative 4, negative 5. And that does look like we have switched the x and y from here. Yes. Okay, that was the world's worst attempt at a smiley face. I think there's an actual smiley face stamp here I could choose from. Let's see. Can she do it? There it is. Now I'm good. All right. Okay, so, today what we're going to do is more of the same. We're going to find inverses. So let me go ahead and pass out today's notes. The first 4 remind us of what happened last week, which is good, because our brains may have forgotten some things. So let's see what you can do with 1, 2, 3, and 4. You look like you don't know where I was going.
I don't, I'm really sick.
Yes, ma'am. Oh, I skipped you.
She needs to organize her textbook. Where does it look start?
All right, so you're giving 1, 2, 3, and 4 a try, please.
Doesn't say anything. You're gonna break it. Isn't it shocking how she shows me her homework every day? I do.
You are going to break the line.
I'm serious. You can do your list soon.
All right, so you're trying 1 through 4? Yep, 1 through 4. Yes. Okay, so if we look at the first one, it is just a line. And our steps for finding the inverse are the same no matter what the function is. So even though it's just a line, step 1 is to switch the x and y and solve for y. So we move the 4 over and we divide by 2. So the inverse, denoted with the little inverse symbolism, is x minus 4 all over 2. All right, this one, we switch the x and y and we solve for y. So we're going to move the 2 over. We undo our cube by taking the cubed root of everything over here and everything over here. So we get the cubed root of x minus 2. We move the 5 over, and that's our inverse. This one, we switch the x and y, and we solve for y. Same steps, every time. Move the 9 over, so that we have isolated our cubed root. Cube both sides. And we talked about on Friday, you would not cube this out. What did I do wrong?
It's supposed to be plus 2.
Yes. Okay, so we will not cube this. We will just leave it like this and move the 1 over. All right, on this one, we switch the x and y. And we solve for y. You are welcome to leave it like this because that helps us to see the x clearly. Or you could distribute. Any questions on 1, 2, 3, or 4? Okay, so on your quiz Friday, we will have inverses.
Thursday.
Yeah, Thursday. Because Friday is Composition Turkey Day.
Bonus points.
Okay?
Not bonus points.
But more points, yeah. Okay? So, yeah. All right. Is there anyone in here that will not be here on Thursday? Carlos, you won't be here Thursday, right?
Oh, yeah.
Yes, ma'am. You won't be here Thursday either. Will you be here Friday? Will you be here Friday? Okay. That'll work. Carlos, you'll be back Friday, right?
Yeah.
Yeah, you don't have foreign language plays?
No,
No? Okay. All
Oh,
right.
those are on Friday.
Yeah. All right. So today we're going to explore 2 more functions and how to find their inverses. We're going to look at quadratics, and we're going to look at square roots. And because taking a square root undoes a square, those are inverse operations. So what happens is, when we look at this, what will we do to solve this? We would take the square root of both sides. Okay, and when we do, we get 2 solutions. We would get a positive one and a negative one. Okay, and the other day we looked at how taking the square root of a square kind of ends up giving us the absolute value function. Do y'all remember that? That we looked at that the other day. So that was pretty interesting. So if we had a quadratic function, instead of the inverse operation, we should say, what would the inverse function look like? And it would be a square root function. All right, now, I say function and I say it lightly here because of what happens when we take, when we find the inverse of a quadratic. It's actually not a function. It is an inverse, but it's not a function. All right, so you guys already know how to do this. We've been graphing quadratics since 9th grade. So negative 2 squared is 4, negative 1 squared is 1, 0 squared is 1, 0, 1 squared is 1, and 2 squared is 4. So if we graph the parent graph for quadratic, it gives us this plain old normal moved parabola. All right, so now let's figure out the inverse of this function. What does the inverse do to the x and y? Switches it. So if I gave you a table, all we do is switch. The 4, the 1, the 0, the 1, and the 4 would become my x values. And the correlating y values, which is indicated by inverse, would be negative 2, negative 1, 0, 1, and 2. So we come over here and we graph this. And the inverse of the original function is this. Now, why was I upset about calling it a square root function? A function has to pass what test?
Vertical line test.
Vertical line
That
test.
does
Does the pink one pass?
not. Does not.
No, it doesn't. So it is the inverse of a quadratic function, but the inverse is actually not a function. So quadratics have inverses, but their inverses are not functions. And we could actually tell from the original graph if its inverse would be a function or not. Now, so I'm going to pretend like I didn't draw that pink one, which is easy for me because I can kind of back it up. If we were just looking at the original quadratic, to be a function, it has to pass the vertical line test, right? Which means any place I draw a vertical line, I'm just kind of sliding it back and forth. Any place we draw a vertical line, at most it would pass through 1 point. So the graph itself is a function. Now, because with inverses, we switch the x and y, when we're looking at the inverse of a function, instead of doing the vertical line test, what kind of line test do you think we're going to do? Horizontal. We're going to switch. Okay? So, if we looked at the original function and we were trying to determine if the inverse is a function, so looking at the original, trying to determine if the inverse is a function, we would use the horizontal line test, and it fails because it passes through more than 1 point. And we saw that when we graphed it. The inverse is not a function. It is the inverse, but the inverse is not a function. All right, so what do you notice about the inverse of f of x? It is not a function. All right, then it talks us through some things. Now, remember we talked about when we switch the x and y, what does that do to the domain and the range? It switches it. So, we so far have studied inverses of lines, cubics, and cubed roots. Well, the interesting thing about all three that we have chosen so far is their domain and range are both negative infinity to positive infinity. So if you switch it, do you notice anything? No, it's the same. So you don't notice. Well, this one is not. Okay? The domain of the original function, the blue one, well, there was no restricted x value. And the range was actually from 0 to infinity because that is the parent graph of a quadratic function. So when we switch the x and y, when we switch to find the inverse, we also switch the domain and the range. So if we look at the pink one, we can see the domain goes from 0 to infinity. You see it? 0 to forever right. And the range keeps going up and keeps going down. So it goes from negative infinity to positive infinity. All right. So what would the equation of f inverse of x be? Now, I have a little issue with this notation because we talked about the inverse is not a function. and we're actually using function notation. It really does give me the heebie-jeebies a little bit. It bothers me a little bit. Because the inverse isn't a function. We can't call it a function. It's not one. Okay? But let's find it algebraically anyway. So to find it, f of x equals x squared. F of x we kind of think of as y. We switch the x and y. So we get x equals y squared. And then to solve this for y, we would merely take the square root of both sides. And when you do, you get the plus or minus. So we get plus or minus square root of x. Now, if we just looked at the positive root x, that is a function. Or if we just looked at the negative root x, that is also a function. The positive one would give us this upper positive graph. And the negative one gives us that lower one. Do y'all see those two individual square roots? Yeah. But together it doesn't make a function. It does make a graph, but that graph is not a function. Okay, any questions about the first one? So, can we find the inverse? Yes. Is the inverse a function? No. It is not. Unless we were sneaky. We can be sneaky. What if we had said, all right, I know this inverse isn't going to be a function, so I'm going to take this function and I'm going to restrict its domain. What if I said we can only look at the right side? Well, if I only look at the right side, when I do the inverse, wrong color. Try again. The inverse of the right side is this part. Does that look like it's been reflected over the line y equals x? Yeah. Or I could also restrict it to where the domain is just the left side and have a function. If I started off with a restricted domain and I just looked at the left side, it would give me, I'm struggling today. It would give me this side. And do you see that it's reflected over that line? So if I restricted the original function, I could have a function. But I have to start with a restricted value. If I don't start with a restricted value, that inverse is not a function. All right. Ooh. Okay, so now we're going to look at the other one. We're going to look at the reverse. If I started out with a square root, what do you do to both sides to solve? Square. Okay, and when we square, we only get one solution. And whenever you square something, that solution is just positive. We only get one solution that's positive. Okay, so if we have a square root function, its inverse, the function that would be its inverse, is a restricted quadratic. It would be a quadratic that has a restricted domain. And we're going to look at it so you can see it. All right, so this is our square root function. G of x equals the square root of x. That is the parent graph. So the square root of 0, 0. Square root of 1, 1. Square root of 4, 2. So we've been doing this for a while. That's why we're going fast, fast. So if we were to graph this, 0, 0, 1, 1, 4, 2. All right, now, the domain of this, I can clearly see, it asks it for right here. The domain is from 0 to infinity, but so is the range. Excuse me. All right, so what will be the domain and the range? of the inverse? Well, the inverse, the range of this becomes the domain of this. They swap. And so the range of this one is the domain of the original. Now, the fact that we haven't shifted it makes this hard to see. But as soon as we shift it, it's really easy to see. If we shift it up, down, left, or right, you can see it clearly. What if I had put it right here? Then when I switch the domain and the range, you can tell. All right. So now let's actually find that inverse. So the inverse would be switch, switch, switch. Switch, switch, switch. So does it look like half of a parabola? Yes. Okay? It's the right half. All right, so let's go find that equation. What does that inverse look like? What does it equal? We know it's only the right half of a parabola. So the important part, after we find it, is to restrict the domain. So we take this, y equals the square root of x. We switch the x and y, and we solve for y. Pretty simple. Square, square. I'm done. So the inverse is x squared. But it's not the whole thing. You must show that we only get the right side. So the domain of this has to be the range of the original function. Okay? All right. Okay, so we have one here. It's a quadratic function. If we kind of think about it, it's a parabola that's dropped down 5 units and it opens up. That's good to think about. I always sketch a little picture. That way the domain and the range are easy for me. So the domain of every quadratic is from negative infinity to positive infinity. The range of this particular one is from -4 to infinity. So, this is a good one, because now we do inverse. And when we do inverse, we switch. So the domain becomes this range. And the range becomes that domain. And now let's find that algebraically. So we're going to swap the x and the y and solve for y. So what do you think we do first? Add. We're going to add 4. And then we take the square root. When you take the square root, you get a plus and minus. So we get positive and negative. Okay, so what this means is my inverse is going to look something like this. It's going to flop over to here, and it's going to go this way. Does that look like it's been reflected over this line? Yeah. This point flops there. Yeah. Okay. The next one. This one is a square root to start with. So it's right over here. It's going this way. And so the domain is from 4 to infinity, and the range is from 0 to infinity. So if we swap them, which is what we do when we find the inverse, you can clearly differentiate between the two now. So let's sound it algebraically, and then we'll look at the graph and see if it makes sense, a sketch of the graph. So to solve this, we would square both sides. Then we would get x squared equals y minus 4. So x squared plus 4 equals y inverse. Now, if I graph that, it would be a parabola that gets both sides. This right here. So, do you see how important it is to add the domain to this? Because if I reflected this over the x equals y line, I don't get both sides. I only get this side. So you must restrict the domain of the inverse of a square root function. You've got to have both parts to be correct. Okay? All right, so you have some to practice for homework. So today we do squares and square roots. Tomorrow we talk about how to determine if any two random given functions are inverses and how to prove inverses. Wednesday we have a kind of a review. Thursday is your quiz, and Friday is composition turn.